name's Daniel Thompson, and this is my talk, Energy from Thorium. And just a quick note to say, I chose that in the heat of the moment because they needed a name for the talk, and it's actually the name of the main blog. The guy who's called Kurt Sorensen. He does a fantastic blog about Thorium, and this is the name of his blog. I'm not affiliated with him, I'm completely independent. I like to do a lot of research into this sort of thing, as I'm sure many of you do as well. And I heard about Thorium a couple of years ago, and it kind of piqued my interest because I've got a bit of a scientific background. I know a thing or two about nuclear physics and things like that. And it was very interesting to me because, unlike most of these things which claim to have limitless clean energy and all that kind of thing, this one was very different because it made sense. It had a lot of stuff about it which I thought, hang on a minute, that really, if I dig a bit deeper in that, that really does work. There's something to that. But there's got to be a catch. So I carried on researching, and 2 years down the line, I'm still looking for the catch, to be honest. And I invite you all to help me look for the catch. If you have any questions as we're going along, or if I've just completely lost you all, feel free, pipe up, let me know. We'll see if we can get there, get our heads around this whole subject together. And I don't want to give you a rose-tinted view of this. I'm independent. This is just what a subject I'm interested in. I don't want to give you a rose-tinted version. I want to give you my understanding and the pluses and minuses. As with any technology, there's going to be issues and dilemmas, perhaps. So we'll try and give a good balance for everyone. So without further ado, people. Most things, we use a lot of energy. Just about everything we do uses a lot of energy. We have historically used a lot of energy. I've thought it'd be nice to have a little brief history of how dependent we are on energy. I mean, we ought to be using energy more efficiently than we do now, but we are actually quite dependent on it. We started with fire. That was some 500,000 years ago, it's reckoned. Estimates vary on that one. But we're actually, from that point, we became very dependent on an external energy source. Unlike any other animal, we are the only ones that do this. We have an affinity with fire. We use it for cooking. We use it for heat. Tribes from all over the world have done this since prehistory. So that was very important. We then developed agriculture and used animals to pull plows and use them for food. We moved on from that. And this is just a rough outline of it's not a complete list, and it's not necessarily in chronological order. But we used animals, and they were very useful until we discovered we could use slaves. Some people would argue we still do that. Then we discovered wind. We used windmills to grind grain and things like that. Water. We used water mills for cotton mills and things like that. Then we discovered coal and how to harness that, and that was the start of the Industrial Revolution. And each discovery of new energy source has marked a movement in the progress of humanity. It's not always for the best, it has to be said, but it has made progress happen for people. And I think with a bit of common sense, we can make it happen a lot better than we do at the moment, I'll have to say that. Then we used coal to make steam, and that was steam engines, much faster transport. Then we had the old oil boom, and that led to all sorts of difficulties because we didn't have that much oil here, it was all in the Middle East, etc., etc. And of course we found nuclear as well. That was found as a source of power. Well, it was known for a while before that, but we realised we could use it for power basically during the Second World War, and that went through to civilian nuclear power because that was obviously the atomic bombs. And we'll look at that in a bit more detail, that what actually happened back then with nuclear, because it was quite a turning point for all of us, and it didn't necessarily take the correct path. Let's move on. Thorium. Right, discovered in 1828 by a Swedish chemist whose name I've left off deliberately to save us all the embarrassment of me trying to pronounce his name. And it can produce lots of energy, and we'll look at how much. Well, this is just a list of some of the highlights of what thorium can do. We reckon it can produce your entire lifetime's worth of energy from about 100 grams of thorium. And we have lots of thorium. We have oodles of it. It actually gets in the way of a lot of industrial processes at the moment. We'll look at that as well. We have a load of it, and it's safe. It's not like a traditional nuclear system. It's the inner workings of it.
What's the traditional nuclear system?
Oh, the traditional nuclear system is based on a solid fuel. We'll look at that in some detail, but it's based on a pressurized system. This is a non-pressurized system, and that's a big deal for this sort of thing. We'll get to that. Environmentally friendly, it actually will result in a net removal of nuclear material from the environment. It's carbon neutral, of course. Very easy to extract thorium. In fact, as I said, it's actually already extracted from many of our things we do today. So we probably will never need to actively extract it. And of course it's realistic. We've known the chemistry and physics for about 60 years now. And the big question, of course, that everyone is bound to be answering, and I just want to deal with this up front. Why haven't we heard about this before? And it's a really good question, and there are some really good answers for this. It was discovered in the context of war, which was the big trouble with this system. It was discovered in World War II by Eugene Wigner at ORNL, that's Oak Ridge National Laboratories. And they immediately realised the potential of this. But what the big problem was with it for them is they were in the context of war, and they wanted to make the A-bomb. And this system doesn't produce any material you can make a bomb out of, and I'll look into that in a bit more detail as well. So they didn't want it. The powers that be said, no, we want the uranium system, which is the other form of fission. There's uranium, well, there's three actually. But the primary ones would be, for this context, uranium and thorium. And yeah, well, the other one, of course, being plutonium, which comes from uranium. So that's what they wanted to do. And civilian nuclear power came from that. And it was actually generated from the whole use of uranium, but was actually, they wanted to use the civilian nuclear power to produce plutonium to make their nuclear bombs. And of course, that's a real good reason not to do the old thorium route. And uranium has, this is a bit counterintuitive. For us, it's completely counterintuitive, but it's very intuitive for them. Uranium is really hard to extract and enrich. And we'll look at enrichment in a bit as well. But basically, it's very hard to, you can take out of the ground all right, relatively, but to enrich it is extremely complicated. You need to be a superpower, basically, to have an enrichment facilities. You may have heard of them. They have big centrifuges to do this. It takes a lot of energy, and there's a big waste of time, basically, unfortunately. And you have to make a solid fuel pellets, which are, again, very costly, very expensive. And the whole nuclear industry based their whole business model upon doing this. And along comes thorium, which actually doesn't require any enrichment, is easily extracted, and doesn't need fuel rods of any sort. It's what we call a liquid based system, and it completely destroys the business model. So money is a big factor in this. That's why we ended up where we are and why we haven't been able to change direction. So moving on, and we already plan to use it, which is the ironic thing. The technology is sat on the sidelines. The Nuclear Atomic Energy Agency, IAEA, they already have the Generation 5 Advanced Reactor program ready to go. Funding is not there for it. It's not going anywhere. But down here, you won't be able to read this, but is the MSR, that's a molten salt reactor, and that is based on thorium, and that is straight off their website. They're planning to do it, but when are they going to do it? Are they just going to sit on the technology until it's too late? Is the question. Now, I'm aware that you may not all be very up with nuclear physics, so I thought we'd do a bit of GCSE physics here. Bear with me. If you want to just check your text or something like that, if you're not interested in this. But I think, so we're all on the same page with this, because this is a very real system. We ought to know a little bit, but there's the periodic table. That's all of the elements.
Oh, God.
And we'll leave that at that. This is an atom. Now the atom is pretty simple. Basically, you've got protons and neutrons in the middle. You've got electrons around the outside. And there's some concepts that we ought to know. And one of them is, what is an isotope? Now, inside the atom, we've got the protons in the middle with the neutrons. They define what the atom is, the protons. That's the number of protons in there. If you've got one proton, you're at the end there at the top, helium. You've got hydrogen. You've got two, you're helium. This one here has got 6, and that means it's carbon. And down there, right at the end of the bottom, is thorium, number 90. It's got 90 protons. Now, the difference with an isotope, you can have a different isotope of each element, and that is the difference of, you have your natural number of neutrons you'll have with it. An isotope has more or less neutrons. That's all that means. So it might have a few more or a few less. And what is radioactivity? And I think it's useful to know basically that some of these isotopes are not stable. They will over a period of time degrade. They will lose a proton or one or more protons. They will split. So most isotopes, the standard elements, are not radioactive. They will just sit there. A lot of these down here are highly radioactive, but not thorium actually. I'll come to that. So basically, radioactive is a propensity to split, and your half-life basically is your measure of how long it will take. If you have a given amount of one of these elements, is how long half of that will have on its own split into its decayed products, which I'm going to come on to here.
Decayed products?
Decayed products, yes.
Well, it just dies then, does it?
It changes form, and it changes form on this scale.
So it's not a decayed product then, if it changes form.
Yeah, and it will quite often decay. Now, over here is thorium. What this is a measure of is, we've got heavy elements here, we've got light elements over here, we've got hydrogen, done that one again. It's the lightest, right over there. We've got all the really heavy elements over here, there's uranium and thorium, things like that over there. And what this is a measure of is the stability of the atom. And these are all vaguely unstable, and depending on, of course, on which isotope you're talking about. But in general terms, this is what fission is. It's taking these elements over here, splitting them, and moving them up towards more stable elements, all the way up to that one there. Anyone know what the most stable element is? It's Fe, which is iron. Yeah, it's the most stable elemental structure. I think it's got 26.
I'm lost in this, mate.
Oh, are we all lost, are we?
Yeah, I am. I'm not gonna lie to you.
Just keep going.
Yeah, keep going. But
yeah, the general trend of this though is we're starting with heavier elements, this nuclear fission, and going towards a more stable, and you can see there's a slight rise. What that slight rise indicates is that you need slightly less of what's called the nuclear strong force to hold the atom together. And this is where we get the energy from, because that nuclear strong force, it's one of those things that, it's like the Big Bang. It's a complete understatement. It's an extremely strong force. And if you need less of it, that is the excess is released as energy, and that's the power behind the atom. That's where we extract our power from. And I kind of wanted to show you this, just to show you, I mean, that's the power from there to there, is the nuclear fission, that up from, that's a slight downgrade there. Sorry?
What are the axes?
This is the binding energy per neutron. It's not really relevant, but really that what I want to get across to you is the appeal of fusion. Now, this from here, hydrogen to helium, you can see on this scale is huge. And you can see why scientists get all a bit funny about fusion. It's a great concept. There's vast amounts of energy, and this is what powers our sun, and will power it for billions of years. But I think I'll come back to this later on. There is big problems with fusion, and we cannot rely on it ever working. It may not ever work, and I would argue it probably won't ever work. So really what we're dealing with is this side going from heavier elements to lighter elements and increasing stability and extracting the energy from it as it goes along. So this is the thorium reactor in a nutshell. This is as simple as I can explain it. Heavy elements are pulverized by neutrons. Now when an atom splits...
What are the heavy elements?
Heavy elements, going back briefly to this, everything down here it will be classed as a heavy element. They've got a lot of protons and neutrons in their nuclei. So heavy elements are pulverized into smaller and more stable elements. And this is a great thing if you can do it efficiently. And we'll look at why solid fueled reactors like we have today can't do this. So they release energy and more neutrons as they go, and that's what causes the chain reaction. As a neutron is released, it goes on and causes another atom to split. So in our thorium reactor, what do we have? We have the thorium in a blanket around here, and we basically expose it to neutrons, and thorium, which is a half-life of 14 billion years, so it's extremely mildly radioactive. If it's, say, half-life for a day, you don't want to go near it. It's very, very dangerous. If it's radioactive for 14 billion years, that's basically the age of the universe. But you could hold it in your hand, it will do nothing. So that's what's in the outside here. And in the middle, we have the core. And what happens is the thorium is split, and it becomes uranium-233, which is a pretty unique substance, and it will sustain a nuclear reaction, causing more neutrons to come out, producing from the thorium more uranium-233. So we don't have to mine the uranium, it produces it itself. And all we're putting into this system is thorium, which is a common element which we can easily take out of the ground. So I call it the locket of nuclear fuel, as in it's a hard shell with a liquid core to it. And the one that is really interesting is called LFTR, that's the liquid fluoride thorium reactor. And this works on a fluoride salt. It's chemically very similar to table salt. It's just that at a high temperature, it will melt and it becomes a liquid. And that will dissolve into it. You can dissolve into it thorium. And this has a very good set of properties compared to, well, this is actually some liquid thorium here. We've got the crystallized cold solid thorium there. And this is just for comparison to some uranium fuel rods. And what's really important with this is that where do we go from there? The point with the thorium is that it's a liquid, and unlike with a solid fuel element, as the radioactive the decay chain happens within a solid fuel, you have to take the fuel out before it's got. I'm going to have to bring that one up. Before it's got down here to the stable elements, you have to take your nuclear fuel rods out because they won't sustain a reaction. You're not letting everything mix. So you're left with these unstable elements here, and this is why you have, from our traditional nuclear systems, radioactive material coming out as waste, having to be buried in the ground for thousands of years, and being just a pretty nasty mess, to be honest. But in the molten salt system, we can get all the way down to stable elements. And we'll look at some of those stable elements because some of them are very interesting and very useful as well. So out of this system, we're basically not getting the radioactive nasty stuff that you would get out of the system that we've used today, which is basically solid fuels.
Still getting uranium as well, aren't you?
We are, but the uranium is always staying within the core. It's never removed, and for reasons which I'll get into later, you wouldn't want to remove it. You can remove it, and you can also take it to start new reactors as well, because to start a new reactor, you will always need a neutron source.
For obvious reasons, you wouldn't want to release it.
No, it's true. It's true.
It's dangerous stuff, isn't it?
It's actually a lot less dangerous than most of the industrial things we do today, and a lot less dangerous
It's
than
been
coal.
proven it's dangerous stuff. That's why people demonstrate about it.
We'll look into that. There is, I know, I understand your point, and I do totally I sympathise. There's a lot of things about.
So you're trying to tell me that there's good to it?
There is, and the reason is because this is a very stable system. It can't melt down. Fukushima cannot happen with this system. It's the physics do not allow it, and this is what I'm going to get to here. It's inherently stable, and it has what's called a negative temperature coefficient. Now that sounds all really wordy, but the point, what that really means, is that unlike with a traditional system with nuclear fuel rods, if a part in that system gets a bit too hot, it will carry on getting hotter, and you have to actively intervene to cool it down. If it was to carry on getting hotter, you would have eventually a meltdown.
So how do you cool it down then?
With a traditional system, you have to have high pressure injectors injecting coolant in. So you have to have a lot of power to inject it into this system. A solid fuel reactor inside the pressure vessel is something like 2,000 psi, which if you imagine your car tire is probably about 30. It's an immense amount of pressure. You need 10 inches thick steel, perfectly formed, to hold that sort of pressure. It's really not good stuff. But this system has a negative temperature coefficient, which means that as it gets hot, the core of the system is allowed to expand slightly, and it will automatically, because there's more gaps between the atoms, it will automatically slow the nuclear reaction down. So it will actually find its own points of stability on its own. We don't need any intervention, and as we'll look at later.
Yeah, we're not in control.
Well, the system will control itself. And
Exactly.
I'll show
That's
you.
what I mean.
I'll show you, and I will show you how that happens as well. Now, so a meltdown is a physical impossibility. Well, not least because it's actually already in a molten state. But an actual going out of control
Scary
can't happen.
situation.
Sorry?
Scary situation.
Yeah, it's, but that's the point of the talk, is to actually open this up to debate, and we'll hopefully reach some sort of consensus on this.
This is all for energy.
Yeah, and the trouble is with our tradition, we do need energy, and I mean, if you look at your traditional way of getting energy, for example, coal-fired power stations, you might be surprised to learn that they produce a lot of radiation. A typical gigawatt nuclear plant, which is the size of a plant that you power a small city with, releases about 5 tons of uranium every year and 13 tons of thorium into the atmosphere. This system doesn't do that. It's all held within a very stable system, and we'll see. We do get things out of this. I've got a small story for you on this as well. I'll try and get back to that. Now, what happens in this system if everything is turned off? If, for example, all the operators are incapacitated somehow, that maybe they've all got food poisoning, or there's a terrorist, or whatever, this system has what's called a freeze plug. The freeze plug is a very, very clever little device. And basically, now this is actually what they built in Oak Ridge. This was actually built by the Americans in Oak Ridge National Laboratories in about 1965. Ran for about 5 years. And what they do, you've got the core here, which is a hot molten salt. It's not under pressure. There's no reason for it to explode or anything like that. That's not really going to happen. And you have down here, this is a drain tank, which is designed to take the fuel when you're not using it. And you have here a fan blowing cold air over a piece of pipe. And very simple. Basically, so long as the core is in there and is hot, you've got a fan blowing cold air over this salt, which freezes, becomes solid at 400 degrees centigrade. So it's locked in the pipe and it's keeping the core there. If you lost all the power to your system and no one was there to shut it off or do anything, that fan would stop blowing, that core that plug of salt would melt, and the whole core of the reactor would drain away into this drain tank, which is designed to stop nuclear reaction. Even in the worst, even inventive. Let's look at the what would happen. Well, in the worst case scenario, if we have damage to the system, what would happen? Now, this stuff, as I say, freezes at 400 degrees centigrade. So you punch, say you threw a grenade at it. Let's say, for example, which
you just happen to have a grenade in your pocket.
Well, yeah. Well, to be honest, throwing a grenade at the system would be a literal impossibility because it's all kept in what's called a hot room, which is designed not to be hospitable to anyone.
A literal
no one will
impossibility. So why say it?
See, this talk is
as if, for example, if there was physical damage to this system, there's no pressure, so it's not going to squirt out. Some liquid may come out and will be caught in the drain tank, but it would freeze as it came out, and it will probably plug the gap on its own. And even if it didn't, I mean, the system can be shut down just by turning a fan off. You know, it's really very. They very deliberately designed the system, and we're very much thinking with safety in mind. And just as a, for example, our current nuclear systems are, you know, they in spite of everything got a pretty good safety record, but their system, as I say, 2,000 psi in this little canister here that's about 12 feet tall or so. And it's a highly inefficient system because you have to have everything running all the time, and then if there's an emergency, you have to actively intervene with it. It's a really bad idea, and there's a lot of really inefficient things go on here. For example, you have these sheets of ice up here. Now this is a fairly small design, so they've tried to make it small because you've got high temperature steam, water in this. It's a water-cooled system. So if there's any leak or gap or problem, the whole lot will flash to steam because it's under high pressure and high temperature. So what they have to have here is sheets of ice, and these are there for just in the event that it flashes all to steam, to try and condense the steam back down so it doesn't blow the top off the whole reactor. When you're having to design a system where you've got a gigawatt or so of heat being pushed out of there, and you're having in the same room sheets of ice, you've got some design considerations that you've just gone completely wrong with there. It's a really bad idea. And in fact, they waste a lot of the energy they produce just keeping those cold. So, absolutely terrible idea. But wait, there's more. There's always more. Nuclear waste. We have quite a lot of nuclear waste building up. This system will eat nuclear waste. You can put it into this system and it will burn it up into useful energy. Many of the stable fission products are extremely useful. And this is basically the waste that comes out of this. We have neodymium. It's a very important metal we use in magnets, high efficiency magnets. We use it in wind turbines. Most high efficiency motors will use neodymium magnets. This is a waste product from this system. Xenon is very useful. We use it in lighting. NASA are desperately short of xenon. This produces it as a waste product, a stable xenon as well, not just the isotopes. Palladium, which is worth £15,000 per kilogram, is a stable element and very valuable. And rhodium, which is worth £150,000 per kilogram, is produced as a waste product by this system. Ruthenium, which is £12,000 per kilogram. And these can be all taken out, sold on the open market. And not only that, but these are used mostly in high-end electronics. And we don't have to mine for these elements, because we actually, rare earth mining, which is what most of these are, is a very expensive and nasty process. This is what China does a lot of. And in fact, thorium is actually found with these elements quite often when you mine it. And so China has, it's been stockpiling thorium for a while, and we'll get into why they've been doing that later. We have other things that it can do. It can desalinate water. Because it's a high temperature system but low pressure, the waste heat from this, you can use to desalinate water. Just as a completely natural byproduct of the way this system works. So you can imagine in a lot of countries around the world, desalination of water will be really useful. And just having it as just a byproduct is a pretty damn good thing. We can produce fuels from it. Ammonia for fertilizers. We can produce petrol and diesel. And all those sorts of things. Petrol and diesel are a bit more tricky to make. There's some advancements need to be made to really make that work. But that's in the pipe. That is a definite possibility. But ammonia can actually be used with a bit of trickery as a direct replacement for things like petrol, and you can run your car on it. And your car becomes a completely carbon neutral mode of transport. And we don't even need to go to the old hydrogen economy or anything like that. We can use cars as they are today as a carbon neutral, green mode of transport. Now they can be small and modular. Now this is because this system is very scalable. We can have big reactors, we can have small reactors. We can go up to a gigawatt or so quite easily, which is, as I say, powering a small city, perhaps. Or we can go all the way down to a megawatt or so, which would which would...
Loud annoying voice.
I was just getting to the good bit as well. So yeah, we can scale down to a megawatt, which we reckon will fit on the back of a flatbed lorry. So it's quite a small system, can be very tightly constrained because you don't need the big pressure vessels. And this means that we can distribute power much better. The national grid system is, you'll be amazed at the amount of electricity that we produce and waste transmitting it over long power lines. Almost half of our electricity is lost that way. With this system, we can have your power plant near where you use it, and you don't have to transmit it as far. It's much, much more efficient. And as I was saying just now, your typical coal power fire station, which produces most of our energy at the moment, produces a lot of radioactive material. I mean, 5 tons of uranium and about 13 tons of thorium, not to mention radium and a lot of mercury as well is released in this, in coal power, in the emissions from these places. They're very nasty and kills a lot of people a year, actually. I mean, you hear about the dangers of nuclear reactors. Compared to coal, they're an absolute nightmare. Coal is a real big pollution problem, and we need to find a better way of doing that. Thorium is also, it's hard to monopolize, and this is going back to what you said about it's found everywhere. I mean, there's large seams of it. There's a seam in Wales, going through Wales. There's large amounts in America. The beaches of India are pretty much made of this stuff. And it's also, as part of our normal mining processes, there's a lot of thorium just left over from that. And when you're looking at the amount that it would take to power the whole world, it's probably going to be about 5,000 tons per year of thorium. And that will come out of a mine about the size, if you were going to deliberately mine this stuff, a mine the size of a football field. One mine, typical, not anything special, just standard. I mean, 12 grams, for every ton of the Earth's surface, on average, 12 grams will be thorium. And that's your lifetime's energy, your energy supply for about 10 to 15 years. So it's got a lot of good things going for it. So we've also, if we don't want to mine it here, and we want to go off and colonize the moon, there's large deposits on the moon. It actually... Sorry? Yeah. Other than that, if we wanted to go up there, we actually have maps on the moon. We can see where this stuff is because it emits a distinctive electromagnetic signature. We can see this stuff. There's loads of it. It's common throughout the solar system. Space exploration will be run on thorium reactors, guaranteed. Online refueling. Most nuclear systems need to be shut down. It's a very expensive, complicated process to not only make the fuel rods, but decommission them, take them out. This, you can put the fuel in as you use it. It's no problem. It dissolves into the salts. It's easy. There's no problem. And of course, you've got online reprocessing as well, which is taking your fission products out. That can be done on the fly. You don't have to shut the system down. They just come out, you know, as a normal, in a normal course of operation. Low maintenance. Because this system is low pressure, making it a lot easier. There is some issues with the salt, which I'm going to get to later, and I don't want to tell you that it's no maintenance. There is some maintenance that does need to be done with these things, but we are looking at a 30-year, virtually no maintenance lifetime for one of these systems.
As long as the nuclear reactor is alive,
Sorry?
As long as the nuclear reactor is alive.
Yeah, that's it. Yeah, I mean, a lot of them were made for about 30 years. They keep them going anyway because the nuclear energy industry actually makes building new ones an extremely expensive process. And particularly when you have the pressure vessel, there's only one place in the world that can make those, and that's in Japan. And it's a vastly expensive thing, and they're booked up till infinity making them. And yeah, so there's only so far we can go with it. China gets in on the game. China, in January or so this year, said that they are going to make a thorium reactor based on the molten salts. They're already part of the Generation 5 advanced nuclear reactors, part of the International Atomic Energy Agency. They're going to produce it on their, pursue this on their own because they're fed up of waiting for us, because we've been dragging our heels on this. And they need energy, and if they can get it from a clean and efficient source, then good luck to them, to be honest. Dr. Zhang Weiheng is heading up the project. This is the chap. He's the son of Jiang Zemin, who was the president of the People's Republic of China. So this is not a small project. He's a doctor and very good at doing what he does, and it's going to make this into a very significant thing. They expect to have a commercial reactor ready by 2020, which seems a long way away, and if I were a betting man, I'd say they'll have it sooner than that. But as I say, the rare earth mining, which I talked about a little while ago, that produces a lot of thorium as a byproduct. Thorium isn't used for anything at the moment, pretty much nothing. So it's just being stockpiled at the moment, and China have been doing this for a long time, with the intention of eventually moving to the molten salt reactor. So they know what they're doing, and good luck to them, to be honest. So the UK effort, as I say, we're part of the International Atomic Energy Agency. This is part of our plans, apparently, but it's not moving anywhere yet. But we do have people like Miss Baroness Worthington. She is a Labour peer in the House of Lords. In a maiden speech earlier in the year to the House of Lords, she talked about thorium, and particularly the molten salt reactor, which is the liquid-fueled reactor. She is, to give this some credentials, and we'll see more of this later on, she was a former anti-nuclear activist with Friends of the Earth, and she's advocating this. So, and literally in September, the Weinberg Foundation was set up, and this is a lobbying group set up with Baroness Worthington and a chap named Kirk Sorensen, who I'll get to later. Weinberg, he was the man that invented the molten salt system. He also invented our current nuclear system, the light water reactor, which is based on solid fuel. He said that was a bad idea. He didn't like the solid fuel system. He just basically rubbished it, but they wanted to use it obviously for the plutonium. He said that the molten salt was a much better way of doing it. And a couple of quotes from him. I can still remember the thrill that came with my realization that the thorium breeder meant inexhaustible energy. And I became obsessed with the idea that humankind's whole future depended on the thorium breeder. And so he was a big fan of this.
And Cameron?
Cameron is insert your own word there, because as I say, we had plans to build this ourselves, but Cameron cut the budget. He cut it off and said, no, we're not doing that. Saving the world is going to be too expensive. So he cut the budget.
He worked for hard enough.
Now then, and I do want to point out some roadblock issues. There is several other nuclear thorium projects on the go, but we need to be looking out for these ones, which basically, as far as I can understand, the current nuclear industry is putting these issues out in order to block progress on the molten salt reactor. They're talking about what's called an accelerator-driven reactor, which is basically a molten salt reactor. It's exactly the same thing, but it's deliberately too small. And it's completely nonsensical, because in order to keep the nuclear reaction going, you therefore have to have a large particle collider, like the Large Hadron Collider in Switzerland. You have to have one of those feeding in protons to actually keep this system going. Fantastically expensive, way overcomplicated, really quite dangerous, and so much so that they actually have to have 3 of these particle accelerators going concurrently at the same time, just in case one of them breaks, because they break quite often. They're not a very reliable system. So it's a really, really bad idea, and they want to do this because it's going to be lots of moolah for them if they get this one going. And solid fuel thorium reactors. As you know, solid fuel is a really bad idea. It leaves lots of waste. It's not like, I mean, when you look at the fuel efficiency of a molten salt system, you can get a nearly 100% efficiency. And just as a question to you, how much efficiency with the fuel do you think a solid fuel reactor gets? Anyone?
40%.
Sorry?
30%.
30%? No. 0.5% usually. And the rest is nuclear waste. The Canadians have a system which produces, they have their can-do reactors. Canadian depleted, deuterium uranium reactor. They get 0.7% efficiency, and they're very proud of that because it's a lot better than what they get with the other reactors. So it's a complete waste of time. They have a project doing that in India, which we'll look at in a moment as well. And of course, the old one, we haven't done it before, which is for a start not true, because we did it in 1965 at Oak Ridge National Laboratories. It wasn't the full system as we'd hope, but it was a molten salt reactor. But they'd like to tell us that we have a system which works to an extent, and we may as well carry on with that. Apparently, is a good idea. Where we left it was the UK situation. So just a quick look at around the world. This system is being looked at all over the place. North America, a chap called Kirk Sorensen, who you should all look at his website, energyfromthorium.com. He basically brought this system back to the fore. When Oak Ridge did their original experiments and built their reactor in 1965, the project was eventually cancelled in the mid-70s. And Kirk Sorensen is actually the guy who went into the labs and asked them, could he see these documents? And he's the one that got them out, got them all digitised, got them back on the internet for the world to see. And he did a fantastic job doing that, and they're all available on his website if you want to look at exactly what happened back in Oak Ridge. But he was with a company called Teledyne Brown. This is a supplier of NASA, and he was their chief nuclear technologist. And he's actually left with their approval. He's left their company and has formed his own company called Flib Energy. Flib the word comes from fluorine. Barium, I think. This is the salt that he's going to use in his reactor, and he's going to have a test reactor by July 2015, which would mark the 50th anniversary of the Oak Ridge experiment going live as well. So he's working on this, and throughout America, in several institutions in America, there is ongoing research into Halsteloid N. And this is an issue that we should look at, and just to get some real perspective on where this is. The molten salt is, if you can imagine a salt as in something like table salt, is a very corrosive thing. It's corrosive to metals quite often. And Halsteloid N was a metal that they developed in Oak Ridge, which was resistant to this.
Sorry, what is it called? Sorry?
Halsteloid N. That's I'll spell that for you. Hasteloy. It's an alloy of several other things, and so they developed this. But this is ongoing research that they're doing still at the moment to make better and better metals that can hold this molten salt. Because at high temperature, the higher temperature you go, the more corrosive it becomes. They still managed to run their reactor for 5 years, so it's not that bad of a problem. But to reach some really, really interesting and very high efficiencies with this system, even higher than what I've previously talked about, if they go to higher temperatures, you can actually get even more out of this system. So to have a metal or another containment, a material that will do that, it will be a big benefit. And there are several other alternatives in the works as well. For example, at the moment they are experimenting with 1 to 2% of niobium, which they can put into as part of the alloy. That makes a very big difference. That's very good for it. And also they can dope the fuel with an element called beryllium as well, and that makes it much less corrosive, and that's a good thing. In Canada, they have their CANDU reactors, which I talked about, the Canadian deuterium uranium reactor. That's a solid fueled reactor, so it produces energy. It's mildly better than the uranium reactor, but it's solid fueled, therefore still waste coming out of it that we don't want. So it's a step in the right direction. At least they're looking at thorium. That's a good start. France have an active program based on molten salt. It's a research program. It's not an active reactor, but they have their own idea. The reactors themselves, there's a lot of options involved here. We can go for one design approach versus another. This isn't one design. There's a lot of options we can have in this. And the French particularly have decided to go for what's called a fast spectrum reactor. And this is where the neutrons are going very, very fast. Usually, to get good fuel efficiency, you'd have graphite inside the reactor core, which will slow down the neutrons. And this actually gets counterintuitively a better fuel efficiency out of it. But they are going for a reactor without graphite in it, and that means that this system is actually going to be particularly good for munching through nuclear waste. But it'll be slightly less fuel efficient. So there's balances to be had in all of these systems. Czech Republic, they have a lot of ongoing research with this. They've actually just announced a whole new nuclear research program. Not based on molten salt again, which is a bit of a shame, but they are working on materials and pumps for molten salt to pump this fuel around, because it's always been continually circulated within the system. So that's what they're doing, and they're the ones that are suggesting that we can get these higher efficiencies with some of the new materials that they're working, because we can work at higher temperatures. Would probably mean a slightly shorter maintenance schedule. I mean, we're talking, the standard life for a reactor would be about 30 years, but maybe a bit shorter than that. But given that you can, when they're fully in production, you can produce these on a production line, it's not going to be that big of an issue, I would have thought. India, they have vast reserves of thorium. Their beaches are practically made of it, as I've said, and they have a solid fuel thorium reactor in the works, known as the fast breeder reactor, which it's looking good, and they're hoping to sell that as well. But it will be answering a lot of their energy problems at the moment, of which they have a lot, because they have, was it 2 billion people there, 1.2 billion or something like that. Russia. Now, the Kurchatov Institute is working with, that's one of their universities out there, is working with Lightbridge on what's called a pebble bed design. Lightbridge is an interesting company because one of the top people there is a guy called Hans Blix, who you may remember from the whole Iraq debacle about WMDs. He was head of the International Atomic Energy Agency and chief weapons inspector. So he's working with them on a pebble bed design. Pebble bed, again, it's a solid fuel system. It's not the same as having nuclear fuel rods, but I'm not a huge fan of that. But that's what they're doing. But just to give this some environmental credential, as we've seen, Baroness Worthington was a campaigner, anti-nuclear campaigner for Friends of the Earth. Stephen Tinsdale, he was executive director of Greenpeace for 5 years in the UK, and he has said there should, however, be one exception to the general approach of using established technologies and designs. The EU should invest in developing thorium-fueled molten salt reactors this is a proven technology. The US operated the molten salt reactor in the late 60s. Craig Bennett, Policy and Campaigns Director for Friends of the Earth, formerly staunchly against nuclear power, all nuclear power. He said it was all a bad idea, but now supports research into thorium, and is also supporting the Weinberg Foundation, which was, as you said, inaugurated by Parliament late this year. And Mike Childs, again from Friends of the Earth, Head of Science and Policy Research. He supports thorium reactors, but warns that we need to concentrate on renewable sources, wind turbines and such, because thorium won't be ready in time. And you can sort of see where he's going, but I think as a long-term thing, we need to be doing thorium as well as doing these things. But he, in principle, is in support of it. So that's some credentials for you. Now, is it a silver bullet? Well, it is very nearly. The whole thorium concept. As I say, when they shut the Oak Ridge project down, they were still in the middle of producing this. They were still in the middle of working out design issues. Do you have graphite in the core? And they had problems with graphite because it tends to absorb neutrons and expand and be a little bit unpredictable. These are all problems that we still need to work on. They're not insoluble. They're perfectly standard problems to deal with. But we need funding, and we need a bit of political and economic focus to actually get them going. Literally, the molten salt program in America was funded by about $5 million. So it was not a lot to get. They had a 7 megawatts plant running for 5 years on $5 million. It's not a completely insoluble problem. We also have lots of options for the pipe work. I mentioned household IM. We can also use carbon composites potentially for this. Again, research needs to be done in this. We could use silicon carbide in this. That's a relatively recent material as well. It's used in a lot of high performance things. Now, there is some waste that comes out of this, but we're looking at the order of 1/10,000th of the waste that comes out of a traditional reactor. This is, as I say, there is some waste, but it's in a molten salt, and the salt is continually processed through a system. So unlike with the solid fuel, you don't have to do any difficult processes to extract it. With solid fuel, what we call reprocessing involves dissolving it in nitric acid, and it's a really expensive and nasty process. And the French do this, and it costs them a lot of money to do it. But with this, any things that we need to get out of there can be reprocessed through a chemical separator, which was in one of the previous diagrams. And it's easy to get rid of, and one of the main ones is called Tectinium-99, which is an alpha-emitting radioactive substance. It's really easy to deal with, in fact. It's not an alpha emission from radiation can be blocked by a sheet of paper. It's not going to be, and there's not a lot of it as well, so it's not going to be hard to deal with. But it would need to be isolated for about 300 years, unless in that time we find something else we can do with it, which is perfectly possible. There's, again, lots of research needs to be done, and some investment in this. So yeah, current design, 10,000 years for isolation for its nuclear waste. Yeah, a significant amount better. Uranium-233, which is the core of the system, it is possible to make a nuclear device out of this, a nuclear weapon. It's technically possible, and I must stress that. But what I also will stress is it will never, ever happen. And there's several reasons for this, mainly because developing a new nuclear device is a really expensive process. You have to have nuclear test explosions and stuff like that. No country is going to invest in that when you can easily get uranium-235, or plutonium, from other sources and make your nuclear device out of that. There's already plans that you can download off the internet to do that. You know, they're not going to develop. They're not going to develop a new weapon that uses uranium-233. And also, there is also the small problem of uranium-232. This is inevitably contaminated with uranium-232. This uranium-233. That's an isotope of that isotope. If you know what I mean. They're both isotopes, but one's got one less neutron. And down the decay chain is a isotope of thallium, which is going to emit hard gamma rays. And so this uranium-233 is perfectly safe when it's inside the reactor, but you wouldn't want to take it out or steal it or make a weapon out of it, because this thallium would likely kill you fairly quickly. But the whole system is designed so that never happens. It's all within a catchment area, within the catchment system, with all the appropriate shielding inside a hot room, which no human will be able to go near. So the idea that we'll be using the weapon is just nonsensical. It wouldn't happen. It pretty much couldn't happen. It's also too cheap. Unfortunately, the whole, as we said, the nuclear energy industry is based around the extraction of uranium and the enrichment of it. That's really expensive, and that's their entire profit is done in that. They used to sell nuclear reactors to governments at a loss, so they could lock in the long-term fuel fabrication contracts. So if you've got a system that has essentially free fuel, it's too cheap to actually put a price on it, really. I mean, particularly when you've got byproducts that are going to pay for that 1,000,000 times over anyway. The economics, we seriously need a new style of economics to deal with.
I heard that back in the day, they were promising us free electric by 2000.
Yeah, exactly.
I don't know if these are the ideas.
Exactly. This is exactly what it was. It was the breeder. This is what's called a breeder reactor. It breeds its own fuel, and the concept of that is that you're taking what's called a fertile fuel, which is thorium, but to make that into an actual device, you need the actual fissile fuel, which is currently uranium-235. That's the only natural fuel that will cause a nuclear reaction. And that's very rare, because this is all left over from when the solar system was born, and all of the stuff that was fissile has radiated away now. And all we're left with is a tiny amount of uranium-235. So if we can take common elements like thorium and turn them into a fissile material, this is the way the uranium-233 comes in, then yes, we have virtually free fuel, free energy, and then we get too cheap to meter, as you say. And this is exactly what they were talking about. Our current system we use at the moment, you're basically burning gold. This uranium-235 is exceedingly rare, really hard to process, and just insanity to do it like that. And this is what I hope with the talk is I want to show people that there is hope for the future. It's far too easy for people to think that we're going to run out of fossil fuels and we'll live in Mad Max world or whatever. That's not necessarily how it's going to happen at all. If we went with a system like this, we could have a future. Who can imagine? It could be a lot better than we have at the moment. But our economic system is the real problem. This is it's an economic problem. Our economic system doesn't support doing something like this. We need to have our energy system as well as our money supply in public hands for the public good. Both of these systems are intertwined, and the money system being in private hands has caused this to happen in many ways. It's hopelessness of our eventual demise into low energy, run out of fuel economy. It will obviously breed apathy towards making a real change in this world and actually fixing the real problems. Money being in my mind, the primary one. If we have that hope, maybe we can get our focus on actually fixing that problem. Whether we do this system now or not, but we know it's there as a possibility. And also energy is a major lever of top-down control. You look at energy prices now. We have a recession at the moment. Prices are soaring. We actually have a reduction in the use of fossil fuels at the moment because people are driving their cars less. We don't have a particular supply problem. It's the speculators on the markets who are allowed to raise the price of energy. And with a molten salt system, your fuel costs are negligible. So I would hope that using energy as a means of controlling people would be a thing of the past and be assigned to the history books.
Hopefully that with the rise of fuel costs, less people will drive and then the emissions might go down.
Well, potentially, yes. Yeah.
But again, the rich
yeah. But we're just delaying the inevitable, and that is peak oil. What's going to happen when the oil runs out is the question that everyone is asking, you know. And we need to plan for that.
Yeah.
Now, there is alternatives that people do talk about, and I get this a lot, and I just want to deal with a few of the big ones. Fusion is unbelievably hard to do. Fusion is what powers our sun. We could, it is said that we could make a power reactor out of fusion, but it may never ever work. And I want to just briefly say why I think that is the case. When a neutron is what splits in a fission reactor. It's splitting a large atom into a smaller one. When you're dealing with nuclear fusion, it's a very different kettle of fish because you're trying to fuse two charged particles together, and charged in the sense that you have electrons surrounding a core which is protons and neutrons. The protons and neutrons are positively charged, the electrons are negatively charged. When you have the two negatively charged shells of the atom trying to get together, they really don't want to go anywhere near each other. And the two cores of the atom, the actual atoms themselves, they're positively charged. They don't want to get anywhere near each other either. So you need to have massive temperatures and pressures to actually get them to fuse together. And to actually do that on Earth and actually get a net energy output is a really tall order, and the maths do not work for it, as far as I'm aware. And we'd need a seriously, outlandishly different breakthrough to actually make this work. As far as I'm aware, not ever going to be a viable proposition. Sure, I mean, that may happen, keep researching it, but for the amount of money we spent on on fusion research, we could have built God knows how many molten salt reactors. We've wasted vast amounts of money on it. We don't need to be doing that anymore. Cold fusion, this came about in the late 80s. It made a big fuss because they claimed that they could get energy from this effect. But for a start, cold fusion is actually a nuclear effect. It's not fusion. It's a very different thing. There's some Italian scientist, Rossi, I think is one of them, is claiming that he's got a system that might be able to produce a net energy output. But they haven't been able to demonstrate this. It's not reliable.
They did demonstrate it 3 days ago.
Did they?
Yeah.
What sort of energy output did they get?
I can't remember, it only half functioned, but it was successful.
Yeah.
It's been successful in 3 tests now.
Yeah.
This one a few days
but
ago was
making it work reliably, as I understand, is a real problem for them. They're having troubles, making it.
Yeah, he's been at it for years.
Yeah.
But, I mean,
and he will probably be at it for many more years.
It's going into production, his thing. That was the meeting 3 days
enough.
ago. And this company, unknown company, has bought the rights.
But the point I'd like to make with this is, even if cold fusion worked, and even if fusion worked under the best case scenario, they're still nowhere near as good as a molten salt system. They're nowhere near as fuel efficient, and they will still produce byproducts themselves. And I mean, the cold fusion works on lithium. You have to mine the lithium, and then it's useless and it's not really viable for. I mean, what we're looking at with the molten salt is a system that is potentially going to power the world for millions of years. It's really there's no reason why we shouldn't be able to do that. It's not going to produce, we're not going to run out of any particular element of it anytime soon. So literally, possibly millions of years of clean energy out of it. And I don't see that happening with coal fusion. I'm afraid it's, if they make it work, they make it work. It's brilliant, no worries. But I don't see it really happening.
Is hydrofusion about carrying that as well?
Hydrofusion, as in fusing hydrogen atoms.
Yes.
Yeah, that is nuclear fusion, pure and simple, as far as I'm aware. Yeah,
Right.
there's fusion of light hydrogen atoms. Yeah. Actually, fusion of the hydrogen atoms is actually spectacularly difficult. So they don't even bother doing that. They take slightly heavier atoms and try and fuse them instead, because that's a lot easier. And they can actually do that, in their big tokamak reactors or whatever they try and build out there. I hate to say it, but I think it's a waste of time. Geothermal. Now, geothermal is an interesting one. It's a very sensible idea in certain parts of the world, particularly Iceland. But it has troubles dealing with mass energy production, particularly because as you actually extract quite a lot of heat from the Earth to actually produce energy, you actually make a cold spot where you've drilled your hole. And I don't know if anyone saw the news earlier about when they were doing the fracking up in near Liverpool, causing earthquakes from drilling holes. This is the problem you get with geothermal as well. So you'll be having to drill a lot of holes because you're making cold spots each time. And you will be able to extract energy, but not for a very long time, not very efficiently either.
They're doing one at Leader project in Cornwall.
Are they?
I think they did a trench down there. Someone was talking about it a while ago.
Yeah.
One of our other meetings.
All right. The trouble is with them is they don't scale up. Yeah, you can do them on a small scale.
Yeah.
That's fine. That's the heat will replenish that from the core of the Earth. But it wouldn't really work. And one interesting thing about geothermal is it is already powered by thorium. The core of the Earth is molten. It's a liquid core, and it's actually powered by the natural radioactive decay of thorium and uranium. That's the majority of the actual heat from the Earth actually comes from them. And so nature has already done this molten salt reactor. Our planet is a molten salt reactor. I mean, and I don't know if anyone knows what the core of the Earth is made of. Anyone?
Crystal.
Someone said iron. It's actually made of iron. And I don't remember from the. No. Let's just take quickly back to this one. Iron is right there. It's the most stable atomic thing. And this is what the Earth has done: is it's taken these heavy elements and made them into iron, because that's what it does. It's a molten salt system.
Does that mean the Earth will eventually sink as it gets heavier?
Sorry?
That's a joke question.
No, it won't. In fact, actually, we're fantastically lucky to have this system going on underneath our feet. We wouldn't be here without it, because biological processes and natural processes actually trap carbon from the atmosphere, carbon dioxide, in the rocks and in sediments. And this, over millions of years, is subducted by plate tectonics into the core of the Earth and is returned into the atmosphere via volcanoes. And this is fantastically important. It's called the carbon cycle. Without this process, we'd have lost all of the carbon dioxide from the atmosphere many, many years ago, and life would not be here. We wouldn't be here without this system. So the Earth we're fantastically lucky to have this already as a system. And of course that's what powers geothermal as well. So that's an interesting side note. But just so you don't think that I'm anti any other of these alternatives, solar roads is a really good idea. I read about this the other day. You can actually, if you take a cheap solar voltaic cell, that's the word, You can actually, it doesn't have to be spectacularly high efficiency, but you can make roads out of them and generate electricity. It's there, and other forms of solar, of course, as well. But they're a good idea. But I think we should have a mix of these things. So we'll come to that. We'll get there when we get there, I suppose. In conclusion, it is the most abundant energy source known to man, by far. It can be harnessed efficiently and safely. It's suitable for long-term, millions of years use. And we really can power the world with this for millions of years. It's safe to say that thorium will be the power behind humanity's future, and we have two options from here. We have continue to screw up our environment and use up all the oil until it's all gone, or get thorium energy working now before it's too late. And that is the basis of it, I think. And that is the end of it.
Has anybody got any questions?
Go for it.
I've got about 10.
Yes.
You said that the nuclear reactors that are in place now are like 0.5% efficient.
Yes.
And the one in Canada is 0.7.
Yes.
What is the efficiency of the thorium?
It's very nearly 100%. Very, very nearly. There is some products that we take out which mean it isn't 100%. But what you're looking at there, that 0.5 or 0.7% efficiency means all the rest of that, above that, is just waste. It's nuclear waste. So that's why they're a big blight on this earth at the moment, the nuclear reactors.
How far away are we actually from building a workable, usable thorium reactor if we got going today?
If we got our heads together and actually got the political will to do it, we could do it within a very short space of time, I'm sure. The Chinese reckon they'll have theirs by the year 2020, and Thompson reckons they'll have his by 2015. Right. And his will be a test reactor. It will be going live in 2015, so it won't be a commercial reactor. But it's ready to go virtually. All the hard work and all the big discoveries have been made now. Now it's a matter of fine tuning and resolving the peripheral issues.
So probably shorter period of time that we'll be able to build a brand new uranium reactor from scratch on the planet Hinkley Point.
Well, yeah, I guess.
They're talking 15 to 20 years to build them?
Yeah, possibly, yeah. I don't really know the nuclear energy industry that well, but
it takes
I'm
about
sure
15 years to put one online if you start today and you want to
funding. And you have the problems. For example, I was saying about the pressure vessels. They're massively hard to make. There's only one place in the world that can make them, in Japan. Yeah. And they're booked up till infinity for making new ones of these things. So
if they,
we'd have to wait for them to go.
As well. There's not enough uranium to build.
Yeah, absolutely. Yeah, uranium 235, as I say,
die mining
is a very rare substance. Uranium 238, which it's mixed with, which is why we have to separate it, is quite common, and we can also use that in this system to use the common version of uranium, what we would tend to call depleted uranium, when it's been through an extraction process. We can use that in the system as well.
Okay. My big thing about Truthjuice is what can we do to make this happen? Solutions.
Keep the camera.
Yeah, absolutely. That's a good start. Do some research for yourself, I guess, and tell people about it. Get the word out there, because there are so many people, even within the industry, who do not know about it. It's unbelievable, really. The lack of knowledge about it. It's not taught in schools. It needs to be taught at least when people do their master's degrees and things like that. That will be a big step forwards. And
pressure of the government.
I still maintain that it's really our economic system that is the big roadblock to this happening. sort the money out, stop working on a system of usury to run a country, and, and maybe we'll have half a chance. Sorry,
Are the nuclear reactors able to, like, are you able to stop using nuclear and then put thorium in the same place? So it saves tearing
You mean
down.
in our current reactors?
In our current reactors, can we like subtly, slowly but surely swap it over, and can they be maintained in the same reactors?
It's actually a completely different design. The internal workings of a current reactor, nothing like the molten salt
That would be a
system
shame,
at
because
all.
then we could have like recycled the buildings and stuff.
Well, yeah, I think we can decommission our current nuclear reactors and yeah, exactly, and put the nuclear material from those in the molten salt system, and then you've got a good startup material. Because something I should have added in the talk is that you need a fissile material to start the system off. We do have that. Nuclear bombs are a fissile material. We can decommission those, put them in this, and that's your fissile material to start it off.
We're meant to be decommissioning some nuclear bombs in the near future anyway, aren't we?
Yeah. And also, I think there was a story that we have 100 tons of plutonium sat around doing nothing at the moment in this country. You know, we could use that as a fissile startup material. You know, so.
They should make something like that. You know, like the nuclear waste you get.
Yeah.
Can it not be used at all? That's it. It's done. There's nothing left with it.
From this system.
Well, no, from like nuclear.
From the traditional reactors.
The current system, yeah.
Yeah. Well, it's basically you can reprocess this. This is what they do in France. Is they dissolve these nuclear fuel rods in nitric acid and try and extract all the component elements. It's really expensive, really complicated. This is to separate out all the bits. But we could just put them in the molten salt system, and it will dissolve it away, and you'd extract the energy content and get down to stable fission products.
So you take the core rods out and just stick them into the.
I'm not sure, to be honest. Potentially, they are.
You make one, and I just set it up like as a demonstration outside the nuclear power plant, and then just sort of like a recycling hole.
I think there's a bit more coding.
You've only recycling plant outside it. Yeah, turn on you chop your thorium plant in the back, like.
You mentioned China were interested in.
Yes.
I think I missed what you said. When did they expect to have one?
2020. They reckon they'll have a commercially available reactor. So that'll be built, presumably on a production line. So that will be able to be sold around the world.
I've read recently there's quite a few people designing different ones in this country. It seems to be quite a hub for thorium reactor development.
Yeah, not enough though. I mean, there's ongoing research into. We looked at briefly the subcritical reactor, the one that needs a particle accelerator to work it. Absolutely terrible idea.
Yeah.
Vastly too complicated, vastly too expensive. Right. Waste of time. Yeah. So yeah, I mean, they might get some interesting science out of it. They might be able to do some along the way to some materials research or something practical. Yeah. But otherwise, it's not going to be of much good.
Any other questions?
Do you think if we don't stop producing CO2, we may as well just forget it?
If we don't stop producing it?
Yeah. Do you reckon the whole CO2 thing is
the CO2 is the carbon cycle will run itself whether we're here or not, or whether we're producing.
Yeah, so do I.
Yeah. So yeah, I wouldn't worry about that.
As I mentioned earlier, it takes sort of 15 years to build a uranium plutonium reactor.
Right. Yeah.
How long roughly?
Once the system is designed and built, once we have the design, you can literally build these on the production line. So you could be producing several a day, probably.
Like cars.
Yeah.
Almost.
Exactly. Yeah.
It's not specific engineering. It's not high-tech engineering.
Well, it is still high-tech. I mean, it's not something you'd be doing, with a welder and a hammer and stuff like that. It'd be it'd still be very specialised process still.
Yeah.
But it would be able to be mass produced. A current system you cannot mass produce it.
Right.
You have to.
That's what I was trying to get to. Really.
With the current system, you have to do things like you have to find a water source. these things need
That's
a
what
lot
they-
of cooling,
that's what they
cooling,
they
yeah,
see, really, yeah.
and you need to divert a river potentially to run a traditional
Like they do
system.
generally.
Yeah, with the thorium system, it's self-contained. You don't need any water source. You can build it underground if you want. It uses high efficiency gas turbine instead of steam, so it's a lot better efficiency there, and you get to not bother having it above the ground. You can just have it out of the way if you want.
Could you scale them down to like individual vehicles and stuff like that?
I don't think that'll be practical. No, I mean in theory you probably could, but I don't think that anyone's going to suggest practically doing that. The best way of doing it really is to take is to have some of these reactors dedicated to producing things like ammonia. Ammonia is used in fertilizer, and you can also use it to produce fuels for cars and things like that. It's very high energy density, and you should be able to produce it on par with current production of oil-based fuels. So that would be a direct replacement.
We can
for that.
produce pretty much free electricity. I'm sure.
Well, yeah, exactly.
I'm sure electric cars.
The economies of scale do come into this, and you should be able to produce it at lower and lower and lower costs.
Yeah. That's what question I was talking about. We were talking outside a little bit earlier about different types of reactors for different parts of the process.
Yes.
Do you want to explain that to them? Because I thought that was really interesting.
Yeah. I forget exactly what we said about it, but the basis is that this is a very open system. There's a lot of different configurations that you can use. For example, you can have a configuration like the French do to actually munch through nuclear waste more effectively, and you can tune it to, for example, to produce more of the uranium-233, and this will be your startup fuel for your next reactor. Or you can tune it back again to actually use up more than it produces, or have a balance. So there's a lot of options, and there's a lot of configurations that can be used in this. A particular research at the moment is the graphite that's in it. Graphite is one of those tricky issues that because it reacts with the nuclear with the neutrons, it tends to swell and contract slightly. So there is issues to be dealt with that, and there's different configurations that we can use with that. So hopefully we come up with something that works really well and lasts a long time as well.
Yeah. Okay.
All right.